Okay, good morning, everyone. So let's continue on with our discussion of chapter 3, inductors and capacitors. I believe we stopped, well, let's see. We stopped right at the physical construction of an inductor. Right. Okay, so any questions? Any questions about any of the material we have covered so far? All right. So moving on. Just a few examples of what a real life inductor would look like. The top three are known as toroidal inductors, specifically for high current purposes. I have three kinds, and I like to show these specifically to show how the number of turns and the physical construction would change the value of the inductance as well as the current carrying capacity of that coil. Okay, so if you take a look at the first one, all three of them are toroidal, by the way. All three of them are toroidal. But if you look at the first one, its value is only 10 microhenry, right? 10 microhenry. So it's, it's on the low end or the low end of the values for an inductor. But if we think about the equation, what do we see? Inductance is directly proportional to the number of turns. And here you can see the number of turns are much less, quite evident. Compared to the second one, which has a thinner wire than the first, but it has more number of turns. Okay, so the inductance level is high. Inductance level is high, 1 millihenry compared to 10 microhenry. But the difference is right here. The current carrying capacity of the first one is 10 amps, which is a huge amount of current. Second one, thinner wire, and so it's only 1.3 amps, right? The thicker the wire, the larger, the higher the current carrying capacity or capability of that conductor. Similarly, if we compare the third one, now the size is much larger. It's a thicker wire, not as thick as the first one, slightly thicker than the second one. You have higher number of turns. So it has the same amount of inductance, 1 millihenry, but the current carrying capacity is still much less than the first one. Okay. Also, 6 milliohms versus 400 and 300 milliohms. So resistance R is defined as rho L over A. L, of course, is the length of the wire. A is actually the cross-section area of the wire. So the thicker the wire, the lower the resistance, right? So inductor number one right here on the left has a much thicker wire, so it has a very low resistance, 6 milliohms, compared to the two on the right, which are much thicker wires, which have like 400 milliohms and 300 milliohms. So huge difference. Again, this is just to illustrate how the physical material, and construction of the inductor affects not only the inductance level, but also the current carrying capabilities of that inductor. All right. Does that make sense? Right. And then these two are in like smaller scale inductors, which you can use in, well, I mean, obviously we can use all of them in PCBs, but typically if we're creating like electronic circuits where you have need for a smaller inductor, that's where we would use the phenolic ones or the ferrite core ones right there. And they look like resistors, right? The packaging looks like a resistor, but it's an inductor. Okay, so just a couple of different types of inductors that you can find in real life. Now, the equation for the voltage and current of an inductor is given by V is equal to L di over dt. Okay, so far in resistive analysis, we looked at voltage and current equations that were linear. right? We did not have any time-based or time-dependent variables. But now we are talking about energy storage devices. So energy storage and energy discharge takes a finite amount of time, right? It's not instantaneous. It takes a fixed amount of time for the energy to be imbibed into the inductor and the capacitor and then released back into the circuit. So the voltage and current relationships have a time dependency. Okay, so the first equation that we're looking at is the equation for the inductor. Inductor equation V is given by L di over dt. Some of the other notations you might see is a subscript of L. And all that is doing is, it is basically telling you that the reference for that current is for that particular inductor. If there's more than one inductor in the circuit, you might have L1, L2, L3, and then this would become IL1, IL2, IL3. So that subscript is just a notation identifying a specific inductor. Also, as I said, the voltage and current have a time dependency, so they are functions of time. So oftentimes we also use these, where I would say it's VL of t is equal to I DIL of t over dt. It's the exact same equation, it's just 2, 3 different ways of writing out the notations. They all mean the exact same thing. So the subscript notation simply tells us it's identifying an inductor. Here it's simply telling you it's a function of time. With or without the function of time or the subscript, the equation is still the standard V equals L di over dt. The voltage across the inductor is the first derivative of the current with respect to time. Okay. And when we get to capacitors, you will see the capacitor VI equation is exactly the same, except the V and I are interchanged. Okay, capacitor current is given by the derivative of the voltage. So I is C dV over dt. And you will see that in just a few slides. Okay. So if we have voltage as the derivative of the current, given the voltage, if you want to find the current, well, you integrate both sides. So you integrate V, integrate L di over dt. L is a constant, you bring it outside, take it on the other side, and you rewrite the equation for I, and so we get this. I of t is given by integral of V. So for a inductor, IL, it is simply integral of VL. Make sense, right? Now, the limits of the integral, we say that they are T0 to T. The variable is also T and the limit is also T, but they're two different things. Okay, and again, we will see that when we solve examples. But I want to point this out right now because students sometimes do get confused and how can the limit as well as the variable for the integral be the same, right? So they are two separate things, but we use the same notations for those. Sometimes in books, we would replace the variable instead of t, we would change it to x. Okay, we would change it to x because the limit of the integral is also t. Again, and the reason is whenever we analyze the voltage or current for an inductor or capacitor, we are analyzing it for specific points in time, right? Specific points in time. So here right now we say it's T0 to T. T0 simply means the value at time t equal to 0. And time t equal to 0, well, it does not mean the beginning of time. It simply means the point in time at which we begin our analysis. It does not have any significance beyond that. And you will see this T0 over and over and over again. Okay, so T0 or T equal to 0 simply means the point where we begin our analysis. That's all it means. It doesn't have any significance beyond that. Okay, So oftentimes you might see a problem and says, oh yeah, we applied voltage for like 5 milliseconds, calculate the calculate the current at 5 milliseconds. Well, 5 milliseconds is just 5 milliseconds after we begin our analysis. So 0 to 5, that's it. That's all it means. So more often than not, T0, the value that you would put in there would simply be 0. That's it. And then of course, this T would be whatever value is given in the problem itself. So you would solve the equation, for T as a variable, and then plug in the value that is given to us in the problem statement. All right, let's take 10 seconds. Think over it. Let me know if you have any questions. Any questions so far? Yes. This one, not at the beginning. We want to solve the equation, and the answer that we obtain will be a function of time. So remember, this is I of t. In the same way, here we would have v of t. So I of t would be valid for all values of t from 0 to, let's say, 5. And so if that equation is valid for the entire duration, we can find the voltage or the current at, like, let's say t is equal to 1.5 seconds or 5 milliseconds. So we can plug in t as any value we want. Yeah. Okay, any questions? All right. So then let's talk about this, I of t0. Okay. When we try to find the current for an inductor, remember, current flows to an inductor, it stores the energy in the magnetic field, right? So the assumption is that there might be some initial charge present in that inductor. Okay, there might be some initial charge that might be present in that inductor. So if you want to calculate the total current or the total charge at the end of your analysis, you have to take into account any initial charge that is present in that inductor. So oftentimes we might analyze inductors for a function like this. You might apply something like this equation and then might have something higher. Okay. So if the inductor is applied this kind of voltage, let's say this is an example of voltage, then the inductor would have some stored charge because of the initial applied current. Then it might discharge in the second portion. So charge, discharge, and might charge again. Now at this point in time, if you begin your analysis, then the inductor has some stored charge in here. So when you calculate the current for the time period ending right here, at the end right here, this would be the initial energy that is already present in the inductor, right? If you only analyze for this portion, the last portion, then your answer would be incorrect because you're not adding up this initial charge portion. And that initial charge portion basically is represented by I at t0, meaning we begin our analysis at this point right here. Then we have to add on the charge that was present at the beginning of that analysis portion. Does that make sense? Again, we'll solve examples where you will see that we have to take that initial value into account. Okay. All right, any questions? Any questions at all? Okay. So inductor voltage V is L di over dt, right? First derivative of the current with respect to time. What if current does not change? Meaning if you're applying a battery, the current is steady with respect to time. So if it's steady with respect to time, di over dt is equal to 0. And if it's 0, what can we say about voltage? 0, right? Voltage is 0. So DC behavior or steady state behavior for an inductor is that it behaves like a short circuit. Okay, inductor behaves like a short circuit. Now, we are not discussing the transient portion of the analysis, not yet. Okay, when you apply a DC voltage, let's say you apply a DC signal, which is flat like this. Okay, the inductor will receive the energy from that signal, right? But it cannot instantaneously, if this is the input and this is the inductor output, it cannot instantly jump to this portion. So if this is, let's say 2, the inductor will take some time to actually reach that 2. Does that make sense? So when we say we are talking about the inductor voltage, inductor current, you're talking about this portion right there. And this is transient analysis, which is chapter 4. The exponential rise of the charging and then of course discharging is what we'll study in chapter 4. But this portion is known as steady state because it's reached full charge. Steady state. So at steady state, that inductor behaves like a short circuit because current is allowed to pass through unimpeded. Okay, so we say when you apply a DC voltage or DC current to an inductor, it behaves like a short circuit when it reaches steady state. Okay, before it reaches steady state, we can say that it varies with respect to time because at any given point in time, the value is different before it reaches steady state. Does everyone see that? Right? Yes. Oh, x-axis is always time. Sorry, I should have noted that down. So x-axis will always be time. And y-axis, well, if you're talking about voltage, y-axis would be voltage. If we are referring to current, then y-axis could be current. It could take V or I. Yeah. But again, as I was saying, transient portion is where it is changing with respect to time. After it reaches full charge, the value remains steady with respect to time. The value at any given point in time is always the same. And here, it's still a function of time. That's what we'll study in chapter 4. Chapter 5 is AC analysis. And AC, the input itself is varying constantly, right? So the input is varying, the output or the voltage, the current for the inductor is also constantly changing. All right. Again, then there are different considerations for AC analysis. But for DC, we simply state that inductor, once it reaches steady state, behaves like a short circuit. And so the voltage, if it's a short circuit, then the voltage across those 2 points would be equal to 0. All right, questions? Equations for power and energy. Power, electrical power is still given by P equals to VI. That doesn't change. So you plug in the values for V from the equation for the inductor, and you get Li di over dt. And there's a small derivation, it's there in the book, where you can find the energy, W is equal to half Li square. So the total energy in the inductor is given by half Li square. I is of course the current, the maximum current that was applied to that inductor. L is the value of the inductance. Okay. Energy, of course, is the work that's being done, and hence lowercase w. So this is lowercase, should be lowercase w. Now, if this was an E major class, we do a lot of problems involving inductors and capacitors where we would ask students to solve for like voltage, current, power, energy, all in depth. Non-E major classes, we'll look at voltage and current equations, and we look at, voltage and current problems, and then we'll look at maybe one or two problems involving some energy, but nothing too complex in that sense. Okay, any questions about the inductor? Yes. Yes. Yep. Yep. You simply integrate. We simply integrate between the time interval, sum everything up basically. And that summation gives us, summation of all the slices gives us the total energy either received or dispensed in that inductor. All right, sorry about the construction noise. All right, any questions on the inductor before we move on to capacitors? Okay. So capacitors are so called because they have the capacity to store charge. Okay, they have the capacity to store charge. Physical construction of a capacitor is simply two parallel conducting plates separated by an insulating material. So if we put the two palms of our hands together, they are conducting plates separated by an insulating material, which is air. And so if we try to measure the capacitance between our palms or between our hands, then we would be able to say that there is some capacitance in there. Okay, it's going to be very, very small, but it's there. Okay, so it's two parallel plates separated by a dielectric layer. Dielectric, in other words, simply an insulating material. Okay, insulating material. Dielectric is insulating layer. Symbols for a capacitor. Typical symbol is simply a component with two horizontal lines. Okay, oftentimes you would see something like this with one straight line and one concave. Those are not as common. Okay, those are not as common. Typically, you would encounter circuits where you only have two horizontal lines of equal length. If they're unequal length, then it's a battery, of course. If they're equal length, then it's a capacitor. If you have an arrow through a component, it simply means it's variable. It simply means it's variable. And that is true for any component, whether it's an inductor or a resistor. If you have an arrow through a component, that arrow simply means that the value of that component is variable. You can change the value physically. And the capacitors do not have any polarity. They do store the charge. Again, it's a passive component, so it follows the passive sign convention. If the current enters through one end, that end is positive, the other end is negative. But there are some polarized capacitors that actually have a plus and a minus sign on the terminals. And those are special kind of capacitors known as electrolytic capacitors. So polarized ones, electrolytic capacitors. And the reason they're polarized is because to increase the capacitance with a small area, what they do is they take two conducting films and they roll them up. And the insulating material between the two is a gel. So very, very thin gel. Okay. So when you apply a polarized voltage to that gel, it oxidizes and forms a insulating layer between the two. And so those kind of capacitors need to be connected in a circuit where you have a specific polarity, plus and a minus. They can still work because if you apply an AC signal to that kind of capacitor, it'll still work. But those are the only ones that are polarized. Most capacitors are not. Okay, like inductors and resistors, they do not have any polarity. You can connect them either terminal. So how does it actually work? Well, capacitor has two plates separated by an insulating material. So the first thing you should understand is that current cannot actually go through a capacitor, right? Just simple physics. You have an insulating material, current cannot actually go through a capacitor, at least not physically. Okay, not physically. So in this illustration, you have a voltage Vs that is being connected to the capacitor. Initial voltage across the capacitor is 0 volts. Initial voltage is 0 volts. Once the battery or voltage source Vs is connected to the capacitor, what happens? You have the positive terminal of the battery connected to this end of the capacitor right here. And the electrons in the wire and the plate are attracted to that positive potential. So they start moving counterclockwise. So electrons leave the plate of that capacitor. When an electron leaves, there's an absence of a negative charge. So there is a net positive charge on that top plate. And so now you have a plus positive charge on the top plate. At the same time, the negative end of the battery repels the electrons in the wire and charge builds up on the other side of the plate. Okay, so electrons are attracted and you have net negative charges forming on the bottom of the plate. And when you have a difference in potential, there's a difference in electric potential between the two plates, you have a voltage. That voltage is defined as the capacitor voltage Vc. Okay, capacitor voltage Vc. Now the reason electrons will flow is because there is a charge imbalance. You have Vs over here and you have 0 over here, right? So the electrons will keep flowing as long as there is a charge imbalance between Vs and Vc. Eventually, Vc will reach the level of Vs. Eventually, Vc will equal Vs. If you give enough time, both values will equal. And once they equal up, there's no more charge imbalance. Electrons will stop flowing. And we say capacitor has reached full charge. Okay, capacitor has reached full charge. Full charge. Now, remember I said we have an insulator in the middle, right? Insulator in the middle. So nothing can actually flow through that capacitor itself. Yet there is movement of electrons, constant movement of electrons in this direction, right? There's a constant movement of electrons in that circuit. Even though it's not flowing through the capacitor, there's constant movement of electrons. And when electron flows in a circuit, that is current flow. And which direction does current flow? If electrons are moving counterclockwise, which direction is current flowing? Clockwise, right? Opposite direction of current. And so I is said to be moving in a clockwise direction, which make complete sense because current for a voltage source goes from minus to plus, right? So current should be going up through that voltage source. Make sense? Right? So again, it goes back and ties it back to the fundamentals. So even though electrons are not actually passing through the capacitor itself, current is still flowing because electrons are flowing in the outer circuit. Make sense to everyone, right? What happens when it reaches full charge? Electron flow stops. right? When Vc equals Vs, no more charge imbalance, so no more flow of electrons in the circuit. So I goes to 0. When I goes to 0, there is no more electron flow in there. Now we can say that the capacitor has reached steady state. It has reached full charge, so it has reached steady state. At steady state, if there is no more flow of electrons, there's no more flow of current, it's behaving like a open circuit. Does that make sense? Right? So at steady state, capacitor behaves like a open circuit. And again, I have that in the next few slides. Let's see. At steady state, capacitor is open circuit. Now, I have this slide in there, just to explain the basics or fundamentals of capacitors, but do not get too bogged down into the device, physics of operation. Because what we want to analyze is by using the terminals of the capacitor, right? For every circuit, do not get bogged down into the device operation. Okay, so when it's fully charged, you can remove the capacitor from the circuit itself, and it will hold its charge indefinitely. Okay, it will hold its charge indefinitely. Now, that is for an ideal capacitor. Real life capacitor, a real life capacitor is represented like this. Actually, so even though we have an insulator between the two plates, a real life insulator, no matter how good it is, will always allow some small passage of electrons. Okay, no matter how good of an insulator you have, you can represent it as a finite resistance. That resistance could be hundreds of mega ohms, which for all intents and purposes is it's infinity. Yet real life insulators and real life capacitors will have some finite amount of resistance. That resistance will allow a certain amount of current flow. Okay, and why is this important? Well, for an ideal capacitor, as I said, it will hold its charge indefinitely. But for a real life capacitor, if you want to discharge a capacitor, what do we need to do? If you have a stored battery and you short other two terminals, what happens? If you have a battery and you short the two terminals, the resistance of that short is very close to 0 ohms, right? It's almost practically 0 ohms. So V equals IR. I is V over R. If R is 0, V could be 1 volt, current would be infinite, right? So you release a large amount of energy almost instantaneously. And when you do that, a lot of heat is expelled. And a capacitor only has a finite amount of energy. You take the capacitor out of the circuit and you short the two leads, what do you expect to see? Spark. You'll see a spark. Depending on the size of the capacitor and the amount of energy that is stored in there, the spark could be very, very tiny or it could be big. There are YouTube videos out there, internet videos out there, you can actually see where people actually do it. But again, it's not that dangerous. However, just going on a little bit of tangent, if you do the same thing to a battery, what happens? A battery, I mean, of course, has a finite amount of charge, but when you short the terminals of a battery, capacitor charge is gone in like a few microseconds. But a battery will keep supplying that energy until it's completely depleted. And most batteries would be able to supply that energy for hours, right? So if you short the two terminals of a battery, you have infinite current flowing, battery gets hot. You have the Samsung Galaxy Note 7. Anyone remember that phone that came out a few years ago? And the reason that happened is because, well, in the pursuit of making phones thinner and smaller, they made the battery compartment very thin. So the divider between each of the cells of that battery was very, very thin. And when you connected to a charger, the battery terminals kind of like got shorted out. Each of the cells got shorted out because they were very thin in the middle. And because they shorted out, a lot of the energy was being released all at once. And so when that happens, the battery swells and then it explodes. Anyway, so always safer to use a resistor when you're discharging any kind of component. The resistor could be very, very small, does not matter, right? Again, V equals IR. If you have 1 volt, but you have R equal to 0, I would still be infinite, right? So even if you put a resistor of 10 ohms in there, you are still limiting the amount of current that is flowing through the circuit. Make sense? Right? So any kind of circuit you run, whether it's a LED or a small diode, you always have a resistor in there to limit the amount of current. So you can control the amount of current that is flowing in the circuit. The same concept applies here. You have a capacitor that is fully charged. You plug in a resistor across that capacitor. The capacitor will now slowly release the energy through that resistor. It will slowly release the energy through that resistor. And of course, the resistor dissipates the energy as heat. So it'll slowly dissipate all of that energy as heat. Okay. Now, how does this relate to a real life capacitor? The real life capacitor, as I was saying, will have some finite amount of resistance for that insulator. Even though that insulating material prevents any electrons from crossing through, there will be some small leakage. And that is modeled as a resistor in parallel with that capacitor. Okay, that is modeled as a resistor in parallel with that capacitor. For the most part, any analysis we perform, we always assume ideal components, right? So we don't have to worry about this resistor. But I think this is something that students should be familiar with. In why a real life capacitor cannot hold its charge indefinitely. Ideal capacitors, yes, if we say we charge it to 1 volt, you can keep it for 10,000 years. At the end of 10,000 years, it will still have 1 volt. Real life capacitors, you charge it to 1 volt, you take it out of the circuit, and within a few milliseconds or microseconds, it's gone. And the reason is the internal resistance of that insulator will discharge that capacitor. So no matter how good of a capacitor or how big of a capacitor you have, eventually it will slowly discharge its stored energy through its internal resistance. Does that make sense? Right? So that's the difference between a real life capacitor and an ideal capacitor. Now, again, as I was saying, we don't have to worry about this model at all. Okay. All analysis is hypothetical. It's all theoretical. It's always based on ideal components. All right, let's take 10 seconds. Let me know if anyone has any questions. Any questions at all? Okay, since I'm talking about real life capacitors, I want to go back to the inductor and just point out a real life inductor. So here we are talking about how an inductor is simply made out of a coil of conducting wire, right? A conducting wire obviously should not have resistance, right? When you wind it up in a coil, it'll still have very little amount of resistance. Ideal inductor is 0 ohms resistance. We don't take anything into account. But a real life inductor who's going to come and steal your car from here? Okay, so a real life inductor, even though it has very low resistance, we still have to take that resistance into account. And so we model that as a resistor in series. Okay, this inductor will be called L, and this resistor will be called as RL. Now, RL in electrical engineering is typically used for load resistor, but here RL is simply the resistive portion of that inductor, or resistance of that inductor. You have to keep in mind that if you take a real life inductor and you measure the inductance between its terminals, you will measure some henries or millihenries, depending on what the value is. And if you take the same inductor and you put it across a ohm meter to measure the resistance, you will measure some value of R. Okay, so physically, the component is exactly the same. Physically, it's the same. You cannot separate out the resistor RL from L. It's the exact same coil. Does that make sense to everyone? Okay, it's the exact same coil. So physically, you cannot separate it out. Yet, when we draw the circuit schematic, we have to represent it in some manner. And we say that the resistor is in series with that inductor, in the inductive portion. This would be an ideal inductor, and this would be its real life resistance in series along with it. And when you get to, well, lab 6, if you're taking the lab 6 deals with, well, modeling this inductive resistance. Anyway, that was the real life inductor. Again, for 201, the circuit analysis we perform is all based on ideal inductance. We don't have to worry about the resistive portion of that inductance. All right. But real life inductor has a resistor in series, and a real life capacitor has a resistance in parallel. Okay. All right, so capacitance of a capacitor is simply defined as the amount of charge it can store, right, for every unit of voltage that is applied. So C is equal to Q over V, right? Capacity to store charge, Q, for every unit of voltage that you apply. So Q over V. So Q, the total charge stored in that capacitor, is given by CV. And then I, current, is the rate of flow of charge. So dQ over dt gives us C dV over dt. So I is C dV over dt. We'll see that in the next slide. But that's where it comes from. So capacitance has units of coulombs per volt, but named after, who is it named after? Faraday, Michael Faraday. 1 farad. 1 farad is a huge amount of capacitance. Okay, 1 farad is a huge amount of capacitance. Typically, real life capacitors are like in microfarads or lower. Okay, microfarads are lower. So typical capacitances that you see in circuits would be like, I don't know, 0.1 microfarads, 0.05 microfarads, really, really small. The ones that we use in electronic circuits for like filtering, those are much larger. Like electrolytic capacitors that I mentioned earlier, those would be about 1,000 microfarads or 10,000 microfarads, which is, well, 10 millifarads. So that's a huge capacitor. It's basically about this big. Typical capacitors are very, very small. These 3 examples I have here just shows the significance of this equation. So Q is equal, C is equal to Q over V. So if you take a look at example A, you see that it's trying to store 6 coulombs of charge for 2 volts that are applied across those 2 plates. So the total capacitance comes out to be 3 farads. 3 farads. Now you can take that same capacitance, sorry, not same capacitance. If you want to store more charge for the same amount of voltage being applied, the capacitance value is now much higher, 6 farads. If you want to keep the same amount of charge, but you want to increase the voltage, which is now 8 volts, your capacitance requirement is now much lower, only 1.5 farads. So by increasing the voltage capability of that capacitor, you can reduce the amount of capacitance that is required in your circuit. Okay. And reducing the amount of capacitance, well, that's again a whole different analysis on why we need to, either increase or decrease the amount of capacitance. But I just wanted to have these 3 examples in there just to show how the capacity of the capacitance can change depending on the requirement. Okay, I have about 4 minutes left. Let's look at the physical construction of the capacitor. So physical construction of a capacitor is given by the equation C is equal to epsilon A over D. Greek letter epsilon is the product of epsilon 0 and epsilon R. Actually, that should be 0, not O. 0 and epsilon R. Epsilon 0 is the permittivity of vacuum. Epsilon R is the relative permittivity of the insulating material relative to vacuum. Okay. So epsilon 0, both of them are constants depending on what material we use. A is the cross-sectional area, and D is the distance between the 2 plates, or in other words, the thickness of the insulating material. Okay, so D is the distance between the 2 plates, which is basically the thickness of the insulating material. Now, one word about the area. Okay, this A here assumes that the 2 plates are identical and they overlap at exactly the same points. Okay, so it assumes that they're completely identical in size and they overlap at exactly the same points. But if you have something like this, and where is the area? What area do we choose? The plate 1 or plate 2? Absolutely. We choose only the overlap. Just remember, capacitance is described as 2 parallel plates separated by an insulating material. If you do not have 2 parallel plates, you do not have a capacitance, right? So only 1 plate does not make a capacitance. I should say 1 plate does not a capacitor make. Anyway, so it's always the overlap, right? It's the overlap, and that's the cross-sectional area. Oh, I should not do A that way. That's the area. This is actually a real-life problem in microchips. So microchips, to put it simply, are basically a micro version of a printed circuit board, right? You have components, and then in this case, it's billions and billions of components all in a small silicon chip, right? And all we're doing is making a connection from one transistor here to another transistor there, another from here to there, and here to there. There's only so many pathways you can take around. So what we do is, similar in a microchip, we make wired connections similar to how we build roads. We need bridges. We need bridges. And so if you've ever seen an interchange around a major city, you would see that they're overlapping bridges that go about 2, 3, 4 levels, right? So there's a road that might go this way, there's another bridge that goes there, there's a third bridge going on top, there's a fourth going on top. So microchips sometimes have like 7, 8, 9, 10, even more than 10 layers. And all of those layers are basically conductors. So going from point A to point B. Okay, then let's say you have something going from point C to point D. Let's draw it out here. So you have a wire, and that wire is basically going from point A to point B. You might have another wire like this going from C to D. You might have another one going from here, E to F. Now, all of these are wires. So to separate those wires, you have an insulating film over each conducting wire. When you have an insulating film, guess what? We have capacitances. So there's capacitance every single spot wherever there is overlap. It's very, 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 very small. It's typically measured in picofarads and even femtofarads. But when you have billions of these transistors or connections in one small die, that's a big issue in microchip operation. Anyway, so just wanted to say, oh, well, not say, but give that example of real life capacitance. So in this case, they are unwanted capacitances. So they are parasitic capacitances. Anyway, out of time. Actually, I've gone a minute over time. So let's stop right here, and we'll pick up here on Friday with some examples of capacitors and inductors. And then we'll have homework. I'll make it due on Sunday night for the capacitors and inductors, and then quiz based on chapter 3 on Monday. All right, so I'm announcing well in advance. All right, so yeah. All right, see ya.